Okay, chapter 4.4 Properties of Logarithms and Logarithmic Scales. Okay, there are some properties of logarithms. Let's check the first one. The first one is logarithm base b of xy. This xy is a product. Then we can separate this xy using the logarithm base b. So it would be log base b of x. This xy becomes plus addition. Logarithm base b of y. So if xy is a product, then separate with the logarithm by making it an addition. If inside the logarithm is a quotient, x over y is a quotient, then we will make it subtraction. So this will be logarithm base b of x minus. The fraction will become a minus. Logarithm base b of y. Okay, these are the properties which is not that hard to memorize and understand. And the third property is, this is the one we did in the previous section. If inside the logarithm is an exponential form, then you can move this exponent out. So you can move it to the front. So n times logarithm base b of x. Okay, so far there are three properties, which is simple. And we have to be familiar with using these properties. Okay, next one is, if here's an equation, x equals y. X equals y. Then we can make it a logarithmic equations. So there will be, what we can do is just take logarithm base b on each side of the equation, so that we can write it as logarithm base b of x. Okay, let me move this one a little bit to the right. So take logarithm base b on the right side too. Okay, and the last one. Okay, if two logarithms are same with the same base, logarithm base b are same, then as you can see, this logarithm base b, logarithm base b. So you can set this x and y equal. Then this is automatically x and y are equal. Or we can do this way. Okay, from this, let me write this formula, this equation. Logarithm base b of x is equal to logarithm base b of y. So why don't we take base b on each side? So the logarithm will be the exponent. Logarithm will be the exponent. This will be the exponents of base b. Then by definition, in the previous section, this thing cancel out. So we have x, and this thing cancel out. So we have y on the right side. So this is equal to x and y. So just assume that the corresponding parts are the same. So logarithm b are same. So we should have these two x and y are equal. So far we have reviewed some properties of logarithms. So let's use this one to simplify some expressions. Okay, in exercise 1, this is example 1. We will expand this logarithm so that we will have logarithm expansions. So let's use our properties. Okay, x, y squared is a product. So once we separate these factors, it will become an addition. So logarithm base 5 of x plus logarithm base 5 of y squared. Because in x and y, there are two factors, x and y squared. And for the second term, this is an exponent, so we can move this exponent to the front. So this is equal to logarithm base 5 plus 2 moves to the front, and logarithm base 5 of y. Okay, letter b is a natural logarithm ln. So this is division, but Okay, this is division, so let's make it a subtraction. So ln of e to the square root of y minus ln z cubed. And the first one is also product, e times y square root of y. This is a product, so let's make an addition. Ln e plus natural logarithm of e plus natural logarithm of square root of 5 minus ln z cubed. Okay, and let's write one more time. Ln square root of y. Square root of y can be written as y to the 1/2 power minus ln z cubed. Okay, for the second one, do you remember converting this nth root of, let's say, x to the nth power? Then we can make this square root, this radical, into exponential form. This m moves to the denominator of this exponent m. So x to the power will be m over n. So the index n moves to the denominator of the exponent. So same thing, square root y, then this is square root, so index 2 is hidden, so move this one to the denominator of this exponent. So it will be y to the 1 over 2. Okay, then next, ln e, then this is equal to 1 because ln e, the base is e, so ln base e of e means 1. So ln e is always 1 plus the exponent 1 over 2 will move to the front. So we have ln y, even same thing. The exponent 3 moves to the front, so ln z. Okay, next example is, okay, we have an expression with logarithm that is expanded, so we want to make one single logarithm. So in order to make it single, we have to move this coefficient 2. So move 2 inside the logarithm, then it will become the exponent of x. Do the same thing. And 1 over 2 moves to the exponent of the logarithm inside the logarithm, 1 over 2. Okay, since now we move the coefficients inside the logarithm, so since this is plus, we can put them together by multiplying these two. So x squared times x plus 4 1/2 power. The 1/2 power is a square root, so natural logarithm of x squared times square root of x plus 4. Okay, for this example, the logarithm has base 5, so we can put everything together. Okay, so one is addition, one is subtraction. So let's put this addition together, then there will be a product, x squared minus 4. Before we do this, the second term, okay, let me change this. The second term is, this will be, let's move this 3 to the exponent of 5. So this will be logarithm base 5 y cubed. And the first one stays the same. Last one is also same. Okay, now let's put these two terms together. Since it's plus, let's make it a product. So x squared minus 4 times y cubed minus logarithm base 5 of x minus 2 squared. And this is minus, so we can make these two a quotient. Let's make this one a quotient. So there will be logarithm base 5 of, the numerator will be the first one, and the denominator is the second part, x minus 2 squared. Okay, and then we can simplify this fraction. So let's factor this x squared minus 4. This is sum of difference. To remember the sum of difference, x squared minus y squared is equal to, this is difference of squares, right? Difference of squares. So x plus y, x minus y. So x squared minus 4, this is x squared minus 2 squared, which is a different square, so we can make it x plus 2 and x minus 2. So this will be x plus 2, x minus 2, y squared, and the denominator x minus 2 times x minus 2. Since we have the common factor x minus 2, we can cancel out. So the result is x plus 2 y squared divided by x minus 2. And you don't have to write the parentheses. Okay, next we will learn the change of base formula. The change of base formula. And the change of base formula is this. Here is a logarithm base b of x. Then we can separate this x and the base using the logarithm. So if you see the right side, you can write it as, okay, let me rewrite it. So logarithm, this will be two logarithms in the numerator and denominator. So the x goes to the numerator, and the denominator, this base b goes to the denominator. And the base of this logarithm can be anything, any positive number that is not equal to 1. So you can use any number, a. Okay, a is a positive number but not equal to 1. So this is change of base. So move this x to the numerator, move the base to the denominator. Okay, using this, let's try another example. Okay, if we can use change of base formula so that we can write two logarithms using a quotient. So this 18 will move to the numerator. So logarithm 18 over the log of 3. This base moves to the denominator, and the base can be any number, any positive number not equal to 1. So you can make it, usually if you don't put it, the base is equal to 10. Or you can use different ones. So using a calculator, you can find the logarithm base 10 of 18 and log of 3. Then the value will be something. So you can leave it like this. Okay, let's try another one. Here's the logarithm base 12 of 400. Then this is equal to, the 400 goes to the numerator, so logarithm of 400 divided by the base 12 will become the denominator, logarithm of 12. And then using a calculator, you can find the answer. Okay, this time let's try this example. Okay, this is equal to the logarithm of 27. 27 goes to the numerator. The base 3 goes to the denominator. So logarithm of 3. And we know that 27 is 3 cubed. So we can write it as 3 cubed over logarithm of 3. And this power exponent 3 moves to the front. So 3 logarithm 3 of log of 3. And from here, log of 3, they are same, so we can cancel out. The result is 3. Okay, to graph this logarithm base 2 of absolute value. Okay, let's start with, let's use a transformation. The parent function can be base 2 logarithm base 2 of ln x. The graph of this is, okay, usually logarithm base 2 of x looks like this. When x equals 1, y equals 0. And if we put the absolute value, then this will be an even function, because once you plug in negative x, then this will be logarithm base 2 negative x is same as the original function absolute value x, which is f of x. So this is an even function. That means the graph is symmetric with respect to the y-axis. So it will be something like this. So the graph is composed of these two. And then the next one is logarithm base 2 of x minus 3. So we will translate this graph 3 units to the right. 3 units to the right. So 1, 2, 3. So let me shift this one a little bit more. So actually the vertical asymptote moves to this number 3. So the graph will be like this. This one and this one. Okay, here is a formula that is for the magnitude, finding the magnitude, the Richter scale magnitude of an earthquake. So if there is earthquake, then if the intensity of an earthquake is I, then the formula, the magnitude looks like this. The magnitude is equal to logarithm of I over I0. I0 is the intensity of 0 level earthquake. So for example 5, the intensity of earthquake in California back in 1999, it looks like this. That is 12 million times the I0, the intensity of 0 level earthquake. So based on this, we can find the magnitude of this earthquake. So based on the formula, the magnitude is logarithm of I over I0. So I is given 12,589,254 I0 divided by the 0 level intensity. Then we can cancel out this I0. So what we have is logarithm of 12,589,254. Okay, this is more than 10 to the 7th power. 10 to the 7th power. So we should have 7 point something. So using a calculator, it will give you 7.1. Okay, look at this. This one is this is greater than logarithm 10 to the 7th power. Greater than logarithm 10 to the power, then this is equal to 7 logarithm base 10. Then logarithm base 10 is equal to 1 because the logarithm base 10 of 10. Because the base is 10, so this becomes 1, so we have 7. So the result has to be greater than 7, so it's something like 7.1. Okay, example 6. This time we will find the intensity of the 1999 Taiwan earthquake. The magnitude is measured as 7.6 on the Richter scale. So from this we want to find the intensity. So using the formula, m equals logarithm of I over I0, and m is 7.6. So let's replace this m with 7.6 logarithm I over I0. Okay, from this we need to get rid of this logarithm. So why don't we take 10 as the base of each equation? Because the logarithm, the base of the logarithm is 10. This 10 is hidden. So we will take 10 using the same base. So we will change this one into an exponential form, exponential equation. So the base is 10, the exponents are 7.6 and this logarithm. So if we rewrite it, the left hand side is 10 to the 7.6 power. The right side, we have only I over I0 because 10 to the logarithm base 10 cancel out. Okay, so from here we can find I. I is equal to multiply I0 each side. So 10 to the 7.6 I, and 10 to the 7.6 is approximately equal to, using a calculator, it will show you something like 39,810,717. So this many times of the I0, the initial intensity. Okay, in this example 7, okay, let's compare the intensity of the earthquakes. So one is measured as 9.5 magnitude in 1960 Chile earthquake, and the other one is the magnitude is 7.1 in 1986-89 San Francisco earthquake. Now there's only like a 2.4 difference in magnitude, but let's find out, how many times as intense, compared to others. So using the magnitude formula, let's find the intensity for the Chile. So that is 9.5 is equal to logarithm base I over I0. Let's use I1 to represent the intensity of Chile earthquake. So from this, take base 10 each side. Base 10 each side. Then logarithm, so base 10 logarithm of I1 over I0. Then this is equal to 10 to the 9.5 is equal to I1 over I0. Because 10 to the logarithm base 10 will, okay, this will cancel out. So the I1 will be multiply each side by I0, so 10 to the 9.5 I0. Okay, for the intensity of San Francisco earthquake, that is 7.1. So 7.1 is equal to logarithm I2. Let's use I2 for the intensity of the earthquake in San Francisco. Take 10 as a base of the exponential form of this equation. This is 2 over I0. Then the left side is 10 to the 9.5 power. The right side is I2 over I0. Multiply each side by I0, then I2 will be 10 to the 9.5 I0. So when we compare this, let's use the ratio I1 to I2. So intensity of Chile to the intensity of San Francisco. And that is equal to 10 to the 9.5 over 10 to the, wait a minute, 7.1. Okay. I made a mistake. This should be 7.1. Why did I write 9.5? So this should be 7.1 all the way. 7.1. So this is 7.1. I0, I0. These I0s are cancel out. And so this is equal to 10 to the 9.5. We can subtract the exponents. So that equals 10 to the 2.4 power. 2.4 is 10 squared is 100. And 2.4 is, using a calculator, it gives us 251. So the intensity is, the earthquake in Chile was approximately, this many times. So 251 times as intense as the earthquake in San Francisco. So even the magnitude has 2.4 difference. Actually, the intensity is 251 times intense. It's curious, huh? Okay, in this exercise, let's learn about the definition of the pH of a solution. Okay, the pH of a solution with a hydronium ion concentration of H plus moles per liter is given by this function or equation. pH is equal to negative logarithm of H plus. Okay, H plus is the hydronium ion concentration. So for example, okay, the orange juice. Okay, orange juice has 2.8 times 10 to the negative fourth power moles per liter of this hydronium ion concentration. Then using this, let's find the pH. So the pH of a solution of this orange juice is negative logarithm of H plus. The amount of H plus is 2.8 times 10 to the negative 4 moles per liter. And this is equal to, okay, in this case we have to use a calculator, so it shows something like 3.6. So the pH, so the orange juice has a pH of 3.6. As you see in the other examples, the milk contains pH of 6.4, rainwater contains 4.2, and baking soda has pH of 8.4. So once we write this on a table, okay, the center is, let's say center is 7, then 7 is the neutral. And as you go to the left, then pH level approaches to 0. And then the solution is more acidic. As you go to the right, it becomes more alkaline. So if the pH is 0, then the H plus will be 10 to the 0 power. If the pH is 14, then H plus will be 10 to the negative 14th power. So based on this equation, pH is equal to negative logarithm of H plus. So if it is, let's say H plus is 10 to the negative 8. If H is 10 to the negative 8, then negative 8 moves to the front, so it will be positive 8 logarithm 10, so that is 8. And this 8 is the pH. Okay, in this example, let's find the amount of H plus. So a sample of blood has a pH of 7.3. So using the formula equation, pH is 7.3, so that is equal to negative logarithm base of H plus. So from here, multiply negative each side, then negative 7.3 is equal to logarithm of H plus. So to get rid of this logarithm, we can put base 10 each side. Then the left hand side is 10 to the negative 7.3 power. The right side is H plus. Then 10 to the negative 7 is something like 5 times 10 to the negative 8 power. So that's the amount of H plus. So the hydronium ion concentration of the blood is about 5 times 10 to the negative 8th power moles per liter.